Hey everyone, hope everybody's doing great. First of all, I'd like to thank you all for inviting me to NamCon. It's great to be here, very excited. So let me start sharing my slides and I will jump right into my presentation. Perfect. So today I'm going to talk about Wasm reversing. Wasm stands for WebAssembly, and it's a hot topic that a lot of people are getting into lately. So I thought that why not give it a shot and talking about Wasm. And I have some experiences on different CTF scenarios that I was doing some reversing on Wasm, and why not share my experience so that we can all learn about it. So for the content, today, first we're going to talk about introduction to Wasm. I'm going to give some information on what's Wasm, then we will see the comparison of Wasm with JavaScript. And then we're going to focus on the advantages of Wasm, and we will see it, see how it fits in the web platform. And then we're going to explore the key concepts for us to understand later the demos, which will include some static and dynamic analysis. So we need to understand the key concepts a bit. Then we're going to have two demos. One of them is going to be focusing on creating a Wasm application so that we can understand the full lifecycle. Where does Wasm lie? And then we're going to do some analysis on it. We're not going to install any tool for the first demo so that we can just use the developer tool on Chrome. And for the second one, we're going to do static and dynamic analysis by installing different tools and also using Firefox developer tool. So this is the content, and let's start with first, who am I? I'm currently transitioning to offensive security. I recently accepted an offer for being a senior vulnerable machine engineer. So starting with May, I'm gonna be at offensive security, which is a dream job for me. Previously at HackerOne, still at HackerOne at the moment, and I hold a bunch of certifications. People know me as the OffSec girl because I swear on Twitter like years ago saying that I'm going to get every single OffSec certificate. Now they created a lot of new certifications, but I'm holding a bunch of them, and for a long time I'm preparing for OSCE on more advanced Windows exploitation. Hopefully it's coming soon. I'm getting there slowly. Besides that, my life is pretty much about reversing and exploit development. I can say it's my lifestyle. I really love doing that. And I'm still a CTF for almost like 7 to 8 years. Cool. So after giving a brief introduction on who am I, let's jump right into Wasm. So what is Wasm? Let's give it an intro to it. So WebAssembly is a new type of code that can be run in modern browsers. As I included in here, most of the modern browsers support Wasm, as you can see in here, Edge, Safari, Firefox, Chrome. Not all browsers, but most of the major browsers support it, and it's executed inside JavaScript files. By default, it's actually a binary SAT format, and it complements JavaScript to basically enhance the performance of the web application, and it provides many features and major gains in the performance. So that's probably the most important feature of it. And the code of Wasm binary file can be loaded and executed by the external components, including regular JavaScript files. And it's not primarily intended to be written by hand, but rather it's been designed to be an effective compilation target for low-level source languages such as C, C++, Rust, etc. So whenever you talk about Wasm or whenever you read about Wasm, you will always see JavaScript. So of course there are questions coming then. Is Wasm the replacement of JavaScript? So let's talk about the comparison of Wasm and JavaScript. So the thing is that Wasm provides a big performance gain compared to JavaScript. And with Wasm, you're able to use other languages, like I mentioned in the previous slide, to compile a binary file to be handled with the browser. And since Wasm provides a way to run code written in multiple languages on the browser at near native speed, Wasm is not really here to replace JavaScript at all, but it's basically to work along with the JavaScript to make things faster. I also mentioned here that Mozilla research team stated the fact that Wasm is way faster than JavaScript. So comparing JavaScript and Wasm, each of them has their own limitations and of course their specifications. Maybe we can mention them so that we can understand where do they lie. For JavaScript, it's a high-level language and it's flexible and it's expressive enough to write the entire web application, right? It has many advantages. It's dynamically typed. It requires no compilation steps, and it has a huge ecosystem. A lot of libraries, a lot of frameworks, a lot of tools support JavaScript. On the other hand, WebAssembly, Wasm, it's a low-level assembly-like language, and it runs near native performance, and it provides languages with low-level memory models such as C, C++, Rust, with a compilation target, so that they can run on the browser. So as we can see, Wasm is a different language than JavaScript, and it's not a replacement. Instead, it's basically designed to complement and work with JavaScript. So we talked briefly about the advantages of WebAssembly or Wasm so far. So maybe we can summarize it in this slide very quickly. So the first and the most obvious one is being fast, efficient, and portable, because Wasm code can be executed at near native speed across different platforms, and it takes advantage of common hardware capabilities. So fast, efficient, and portable, and executed at near native speed. This is probably the most obvious one. And the next one is readable and debuggable. So Wasm is a low-level assembly language, like I mentioned, and it also gives a human readable text format, so that you can so that the code can be written, viewed, and debugged by hand, which we will see in the demo later. And last but not least, Wasm is designed in a way that it can play nicely with other technologies and maintains backward compatibility. Cool. So where does Wasm lie in the platform? How does it fit in the web platform at all? So if we go to the basics, a web platform has two parts. One of them is the virtual machine that runs the web application's code, right? The second part is a set of web APIs that the web application can call to control web browser functionalities. And at the end of the day, make things happen. So the virtual machine, the VM, loads and runs the two types of code. One of them is JavaScript, and the other part is WebAssembly. So in the past, virtual machine was able to load only JavaScript, which worked pretty well, of course, to solve almost all of the problems. However, with JavaScript, there are performance issues, especially when it comes to augmented reality, virtual reality, 3D games, video editing, anything that comes to mind that requires a lot of performance and speed. Plus, there are a lot of big costs of downloading and compiling very large JavaScript files. And again, it leads to performance issues. So at that point, of course, Wasm comes in place with its speed and performance support. Cool. So since I mentioned that we're going to go into two demos, I just thought that maybe I can briefly talk about the Wasm key concepts as well, because you're going to see it especially when I'm debugging the Wasm code in the browser. So I thought that maybe you can familiarize yourself with these concepts. So what are the Wasm key concepts? There are several of them. If we start diving into every single key concept or the assembly specifications of this language, it would probably stay here the entire day. So I'm just going to briefly talk about the key concepts so we would be familiar with it for later. So the first one's module. It basically represents the Wasm binary that's been compiled by the browser into executable machine code. The second one is memory. It's basically a resizable array buffer, and it contains the linear array of bytes read and written by Wasm's low-level memory access instructions. The third one is table. It's a resizable typed array of references that could not otherwise be stored as raw bytes in memory. An instance is a module paired with all the stated uses at runtime, including memory, table, and set of imported values. So these are like the brief descriptions of what key concepts are, and the JavaScript API provides developers with the ability to create these modules, memories, tables, instances, etc. And since JavaScript has complete control over how WebAssembly code is downloaded, or compiled or run, JavaScript developers could even think of Wasm as the JavaScript feature for efficiently generating high-performance functions. Since we learned a bit of what is Wasm and the key concept, the advantages of it, the comparison between JavaScript, let's see our first demo on how to create a Wasm application and how to do some basic analysis so that we can familiarize ourselves for it more. All right, so we're going to start by creating a simple Wasm application, and then we will do static analysis to analyze it later. So the first thing I'm going to do is I'm going to create a very simple HTML file, and then we're going to create the Wasm binary and the JavaScript code to create our HTML file. It's going to be a very simple example. So this is our skeleton file, a very simple HTML file. We're going to define an test function here. We're not going to install any tools. We're going to use an online tool called Wasm Fiddle for us to generate the Wasm code, the Wasm binary. So I'm going to write a very simple C program in here with void hello. Let's see, printf. Let's give us the hello world pop up at the end of this. Perfect. So if we click on build, it's gonna create us this Wasm code in here. So we don't want to have just the C code here. We want to include a JavaScript code as well. So I'm going to have this code in here. So the first one is a very simple function that basically converts a UTF-8 payload to a string. It takes two parameters, H and P, and there's a for loop here. Basically, it takes every single character, iterates it, and converts it to a string and returns at the end. It's a very simple function here. And also we created some variables in here. It's basically to initiate WebAssembly binary creation. And it will execute the hello function that we wrote in here in the C code. We built this already. If we want to see it in a binary format, we can just change this one to code buffer instead of text, which will create a binary Wasm code for us. Then we can put this in our JavaScript buffer later. I'm just going to copy this value and we'll go back to my sample HTML file to edit it in a way that I can insert this value. I'm going back. So that's the final version that looks like. We just inserted our conversion function in here. There's a test function that we had initially in our template. How did we fill this function? We included this buffer in here that we just got from this online tool. We already created this Wasm binary code. We inserted in here. Again, we got the exact same code that we before previously. Basically providing the import definition in here in this line. We're creating the puts function here that will pop up the alert basically. All right, that looks like the final code. I'm gonna go to Chrome. As you can see, it created this pop-up alert, which was the intended behavior. That means the code works as expected. I'm saying okay. I'm gonna start my Chrome developer tools by clicking on F12. As you can see, it popped up. So let's see, what do we see here? There's a test.html file that we already created. It loaded the source code, and there's the Wasm file in here. We're going to click on this. We're seeing the exact same data that we got from the Wasm fiddle. If we turn this into text format, as you can see it in here. Very cool. We're going to put a breakpoint in this function, and this one. If you just click on that memory address, you're just going to put a breakpoint in here, and as you can see, it also pops up in here. It will appear and disappear if you click on it. Blue bar means there's a breakpoint put already. So we're going to use a single step execution in order for us to debug the code slowly. So I'm going to click on Control R, which is going to take me to my breakpoint. That means execution successful so far. It paused in the debugger in the breakpoint at the moment. If you can see in here, the stack is empty at the moment, as I did not put anything on the stack yet. If I step over with F10, or I can just click on that little button as well, it's the same. As you can see now, stack has this value 16. 16 is not a variable, it's just a pointer to a memory address that holds a value. We will have a look what this is in a second. You can just go to module. If you remember our Wasm key concepts from the slides, this is exactly how it looks like when you're debugging. So that's why we covered it in the previous slides. So if you go to the memory address, that 16 is basically the memory address that refers to here that holds the value in string hello world. So that's exactly what we're seeing in the 16 here. We step over, so we are in that moment. This call basically for the puts that we included in our back here. If you remember that put, which was gonna pop up the alert. That's exactly what we're referring to here, which we'll call the final function that we want to see to pop up the alert. So if I go over it one more time, or F10, it will give me the pop-up alert. Cool, so that was the first very simple static analysis that we did without installing any tool, basically, using the Google's Chrome's developer tool, plus an online tool to create our Wasm binary. After gaining a bit more information, we're going to jump into the second demo now to solve a CTF exercise here to do some static and dynamic analysis. We will also use several tools so that we can also familiarize ourselves with several tools that would be helpful for you if you want to continue on your journey with Wasm reversing. All right, so we're going to go through another demo now. I'm going to use a CTF flare on 5. So the name of CTF is web to point. We're going to use both dynamic and static analysis to reverse the Wasm binary. So let's see what kind of files do we have. We have these 3 files: index.html, main.js, and also test Wasm file, right? So let's see the index.html file, and as you can see, it's a very simple file, and it just calls main.js. So I'm just thinking all the games happening in this JS file. I'm adding this and I'm checking the main.js file to do some analysis. So when I walk through the file, at the end of this file, you're seeing this function here, unit 8 array. There's like a conversion happening in here, as you can see. So as you can see, it reads a URL parameter q, and it converts it to unit 8 array of bytes. And as you can see here, there are two 0 to 100 bytes of memory block within this Wasm instance. One of them is filled with the array of bytes, values declared at the start, and the second one is filled with the bytes of the URL parameter q, right? The b, as you can see in here. Then we have the match function called with the corresponding arguments, and there's like an if statement here. If the function returns 1, our flag is correct, otherwise our flag is wrong, and it gives us a different emoji. So we need to win, we need to write the correct flag in order to get this emoji, otherwise we get this 1. So I just loaded, I just put it under my web server, and when I run it, as you can see, I'm just getting this emoji. So obviously there is the Q parameter that needs to be written here. If I write a random value, I'm getting that. So I need to correct this flag somehow. So let's see what it looks like in the browser, if I go to F12 for Firefox debugging tool, let me refresh the page again. As you can see, we get the main.js file and also the Wasm file given in here. I put a breakpoint before, let me remove that, then we will go through the file again. So what I'm gonna do is that some people, totally depends on you which environment you're using. I'm gonna just load this Wasm file in JAP compiler. So as you can see here, when I load it, I'm seeing different functions besides the one that we saw in the source code, which was a match function. There are different functions from F1 to F9, and also there's another one, write VC. So when I open it in the graph view, I'm also seeing what it looks like for the function match. It's very similar to the view that you will get in IDA, but I wanted to share a different tool here besides the one that you will probably see in other solutions as well for other CTF scenarios. So I'm seeing which call is triggering this if statement is this call F9 and in here. So I'm gonna look into details of these in a second. I'm just trying to understand the logic behind it. So there was a graph view. If I go to the assembly, we're gonna go through the code to understand what it does. So the thing is that it takes i32 parameters and it returns the i32 value as output. So the thing is that Wasm is a stack-based virtual machine, and there are no registers here. So all operators are done by pushing and popping the values on the stack. For instance, if you're adding two numbers, it's by basically pushing these values, and you're seeing i32 add instruction here, which pops off the topmost two values and then adds them and pushes the result back on the stack. So when I look in the graph view again, we're calling the F9 function, and the value returns whether 1 or 0, and you're deciding which way you will go, and the different emojis return in these two different roads. So whatever check is done, it's happening in the F9 function. So every single character that we enter in here in this parameter will be compared with the real flag, and the comparison is done in F9 function. So what I'm going to do next is I'm going to use a tool called WABT, WebAssembly Binary Toolkit, which provides a lot of scripts for you to use to convert the Wasm file to VAT or the C file, to decompile and try to read the source code. So when I install the tool, you're seeing many scripts that you can use. The one that I'm going to use is Wasm to C, so that I can convert the Wasm file to the C file. So once I run the script, I create the test.c file and I load it in here. As you can see, all these arithmetic operations have been converted into their C equivalent. However, the thing is that some of the functions do not have C equivalent. So the easier approach here is to compile this file and load the binary file in IDA or any other disassembler that you have, so that we can decompile the code, and hopefully we will have a more readable format, which I've done, and I copied it in here. I copied the decompiled code in here. So if you go through the C file that was created by Wasm to C, so there's this call indirect instruction, which will be the corresponding value of the following in the decompiled code. So just after that, there will be a comparison comment in here, which is a character-wise comparison. So I'm assuming this is the part that I'm going to use to find the right flag. So one way to solve this exercise is whether we can
Or we can update this C file a bit because right now it's missing the main function. Or the other thing we can do is we can start debugging already by doing a dynamic analysis on the browser already. So in here, I'm seeing call indirect, which takes a function operand, which will refer to the comparison later. If I scroll a bit down, I am gonna find I32 equal here, which will be the place that we will be doing the comparison. So if I go to the browser again and click on the Wasm file, we're seeing a call indirect in here again. I don't need this one, but I need I32 equal, which is the place that basically makes a comparison. I'm gonna put a breakpoint here and I'm gonna run it with this random value. When I run it, we are post on the breakpoint in here. So as you can see in the previous two instructions, we are getting var83 and var82 and var83, and we're basically comparing them. So let's see in the block what it looks like. When I scroll down until I reach out to 82 and 83, I'm seeing 119 and 97. If I go back to my terminal and I write Python, and with the character conversion, I can write 119. As you can see, it's the W character. And if I write the other value, which was 97, I'm gonna get the value A. A is the value that I put in here, and it's comparing it with W. So obviously, if I continue comparing it in the same format for I32 equal, I'm gonna get every single value for the flag. That's one way to do it. Another way to do it is, let's go back to our JavaScript file. In main.js, I got this uunit8 array values in here, which is basically the Wasm value that we got. We learned how to create this using Wasm Fiddler, the online tool also. So what I done is I created this converter script to put this code in here and convert it one by one, basically with cunit8. So let's run the script to see what it's gonna give us. It gave us this value. I'm just gonna copy that and paste it in my browser. For the Q parameter, when I do this, let's kill the breakpoint so it can execute properly. It's gonna give us the other emoji. So that was just another demo for us to explore different tools, and static and dynamic analysis, and see how it works in the Wasm world.
So that was all the presentation that I have. Thank you so much for listening. Hope you enjoyed the presentation. That was all that I have. Hope you learned about the Wasm and how to use several tools to reverse a Wasm binary. Thank you.